Hello. So, yesterday we discussed this formulation of Lagrange interpolation as uh, normalized product of zeros, uh, zeros of all other nodes evaluated at the node for which we are developing the interpolation function. So, the product is essentially multiplied by equation of roots x minus x I, x minus x j, and then this is evaluated at the ith node for which we are deriving the interpolation function, and that is normalized with respect to that value. And so, the both the conditions of interpolation, that is n I at evaluated at x j should be equal to delta I j. It should evaluate to unity at x I, and it should vanish at all other nodes when I is not equal to j. And once we have this interpolation function, then it can be combined with the function values that we have at specified at these nodes, and just express it as a linear combination. So, L I f I, and that is the function approximation through interpolation model, polynomial interpolation. So, nth degree polynomial interpolation using Lagrange's interpolation model. Now, Lagrange interpolation, as I said, it is very easy to construct analytically, but it is very cumbersome to evaluate beyond the first degree. As you can see, it is it is constructed by accumulating the products of each term. So, nth degree polynomial will require n number of evaluations, and then of course, the normalization, that is division as well. So, it is very inefficient to compute because there are far too many floating point multiplications and divisions, and as we had already seen earlier, every single floating point operation is a source of error, it is a source of round of error. So, the key to reliable and robust computation, floating point computation, is to do with as few floating point operations as possible, and that will also increase the efficiency of any algorithm. Another problem with Lagrange interpolation is that they are global in scope. We just develop entire approximation over the entire range, and if something goes wrong, or if there is any change in data, or if we change the node a little bit here and there, somewhere in between, then the entire exercise has to be started afresh. There is no way we can make use of already computed results if there are any. So, the entire process, for even for one change in data point, the whole process has to be repeated completely from first step. And of course, it is when we talk of numerical computations and efficiency, it is of course preferred if previous computations can be reused for subsequent computations. So, Lagrange interpolation, as I said, it is a polynomial, nth degree polynomial, is only of theoretical interest, and it is very easy to explain how it works. But and because the polynomial interpolation, any polynomial, nth degree polynomial passing through n plus 1 number of points is a unique polynomial. So, no matter which form of interpolation I use, as long as it is a polynomial interpolating through function values n plus 1 number of function values, then it is going to be the same polynomial irrespective of which way I arrive at it. So, Lagrange interpolation, because of its simplicity and elegance in construction, is often used for theoretical analysis and error bounds, etc., but never, almost never for any actual numerical computations. So, to build upon that error, the concern that it is a global polynomial, global scope, and everything has to be constructed afresh, we have improvement on that by using Newton interpolation model, wherein we increase the degree of polynomial, we increase the degree of interpolation. So, the first term is a constant term P 0, it is a constant term, P 1 is a first degree polynomial, P2 would be second degree polynomial, and so on, and so that the nth term is the nth degree polynomial. And that is how we construct this approximation, and gradually, so that we can make use of previous results, and if any intermediate data is left out or it has to be changed, then only relevant point has to be from that point onwards it has to be modified. So, P 0, the 0th degree polynomial, is chosen such that approximation function f hat, when it is evaluated at x 0, returns the specified value. So, it is just the function value that is specified at x 0. So, that becomes the basic constant, just a constant term C 0, let us call it C 0. Now, considering that C 0 is already known, then we define next term P 1 x such that P 1 x returns the value of f of x 0 when evaluated at x 0, and it returns the value of f of x 1 when it is evaluated at x 1. So, we impose this condition, and the way to do that would be to enforce that the coefficient linear term should vanish at x 0. So, it is just x. So, the polynomial model that works out is C 0 plus C 1, that C 1 is still unknown, C 1 multiplied by x minus x 0. So, this first degree polynomial of course vanishes at x 0, and because C 0 has been evaluated such that it returns, it is same as the value of the function, specified function value at x 0. So, it meets that criteria, and now we impose the condition that P 1 x has to be evaluated to when it is evaluated at x 1, it has to return the value of f x 1, f of x 1 that is specified, and when we impose that condition, that allows us to find out what is the coefficient C 1 going to be, and that is what you get. So, by enforcing the interpolation condition at x 1, we can evaluate what is the coefficient, unknown coefficient C 1 going to be, and you can see the pattern here. Now, it is a you can look at it as a difference formula. It looks like a difference formula, and it is a difference formula. So, that gives us another hint, another way of developing the or computing the coefficients of Newton interpolation model by using divided differences. So, what you see here, C 1 evaluated as difference in the function values divided by the difference in the independent variable. So, x 1 f of x 1 minus f of x 2 x 0 divided by x 1 minus x 0. And then next term, quadratic term, is again imposed with the same addition on, we add modification whatever quadratic term C 2 x minus x 0 multiplied by x minus x 1 on top of P 1 x. So, the first degree polynomial, first degree interpolation that we had earlier found, and then again the interpolation constraint is applied, that this second degree polynomial P 2 x has to evaluate to f of x 2 at x 2, and when we impose this condition, then you get the basic coefficient C 2 evaluated at f of x 2 minus that first degree polynomial evaluated at x 2 and divided by these x 2 minus x 0 and multiplied by x 2 minus x 1. So, this is how it is recursively built using previous approximation. So, nth degree term, coefficient of nth degree term would be evaluated by f of x n minus value of the previous degree of interpolation polynomial evaluated at x n and divided by the normalizing factor. So, the Newton form of nth degree interpolation polynomial is given by progressively increasing degree of polynomial term in the series. So, it starts with a constant term, then you add a linear term, then you add a quadratic term, then you add a cubic term, and so on until you build nth degree term. So, that is what the formulation or the conceptually Newton interpolation model talks about, but as you can see here, this is there are far too many, still there are far too many floating point multiplications if we evaluate it according to this definition, the way the Newton form is defined. But if we look at this pattern very closely, we can see that the factors are common. For example, x minus x 0 is a common factor for all terms starting from the second term all the way to nth term, n plus 1th term. Similarly, x minus x 1 is a common factor for all terms starting from third term to n plus 1th term, and so on. So, we can actually minimize the floating point multiplication by recognizing this and rearranging the expression backwards, starting instead of starting from constant term and going all the way to nth term, we can start writing the expression from nth term and taking the common factors and working our way back to 0th term or the constant term. So, that is what we do here, write the expression in the reverse order, and then once we realize that there are too many common factors, it is easy to reorganize this by taking the common factors out, and its number of multiplications drop down dramatically. And this is the most efficient way of computing Newton interpolation polynomial, and this is called Horner's algorithm. Another way of computing recursive evaluation, I mean this is what this is the evaluation of the function itself, polynomial, Newton polynomial, Newton interpolation polynomial, but we still need to find out what is the value of these coefficients, how are these coefficients, what are these coefficients C 0, C 1, C 2, etc. So, these as I said earlier, the computation of C 1 provided us a hint that we can actually compute these coefficients by way of divided differences. So, that is possible by using recursive evaluation of coefficients by using the divided difference of different orders, and C 0 being the 0th order difference. So, that is just the function value at x 0, then C 1 is the first order difference, and C 2 is the second order difference, and so on. So, if we arrange the values, then it is defined, it is very easy to compute, and coefficients can be computed very quickly in an automated almost in an automated fashion. And then the Newton interpolation polynomial can be simply expressed in terms of divided differences. So, here within square brackets f within square brackets x 0, these are the these denote the divided differences. So, one term, that is the 0th order divided difference, and this one is the k plus 1th order divided difference. So, coefficients. So, with this we can this way we can compute the interpolation polynomial and evaluate it very efficiently in any for any particular value of x that we may need by using Horner's algorithm, and we can go ahead with our computations. Now, in the beginning when we were discussing about the Weierstrass approximation theorem, which said that it is possible to approximate any function no matter what its origin by a polynomial approximation over a finite range, and the approximation can be as close as desired. That is theoretically true, because polynomials are an infinite family. I mean the basis infinite basis functions can be constructed. So, theoretically we should be able to find any function which is finite without any singularities and over a finite region. So, we should be able to approximate that function using sufficient number of polynomial terms. But the problem, as I said earlier, it is not specified. The Weierstrass approximation theorem does not tell us about how to construct or what is the criteria for imposing the constraints of polynomial or closeness of approximation, what is how it is to be measured, right. And that actually has a difference impact on the quality of approximation, as we will see just now. So, importance of sampling points. So, where do I choose the sampling points? So, the nodes, if I have a liberty to choose the nodes of interpolation, I mean I can choose the nodes of interpolation, there are large number of tabulated data points, and if I have the liberty to pick the nodes at according to my wishes, according to it is left to us, then it might be worthwhile to see which nodes to choose, so that for a given degree of interpolation, so that we may be able to derive a better approximation. And you may like to look at this particular thing. I mean, this is called a Runge function, that is a rational polynomial. So, it is a function which is ratio of I mean constant term divided by some polynomial term in the denominator. So, that it blows and then it decays as the denominator increases. So, the solid line actually describes the Runge function exactly in analytical form, and the dotted line, I mean the dashed line represents 10th degree polynomial approximation. I mean when we say when we try to approximate, we would obviously inclined to divide uniformly any interval that we are given. So, for example, in this case we have this interval from -1 to +1. So, if I am asked to interpolate between these I mean 10th degree polynomials, so I would just pick up 11 points which are uniformly spaced in this range. That is the first impulse that anybody would do. Now, it so happens that this is not a very sound strategy, although it is easier for us to do that and hope that everything will work out very well, but it so happens that it does not always work out so well. So, the dashed line you can see is the 10th degree interpolation polynomial based on for which the nodes were derived on the basis of equidistant approach. So, you can see that the function value exactly matches at regular intervals. So, the Runge function and the 10th degree interpolation polynomial, they match exactly at the nodes of interpolation, but in between the nodes of interpolation, particularly I would draw your attention to the end interval. There are wild fluctuations between the between two nodes, and that is because of the constraint that has been imposed. It is a very high degree polynomial, 10th degree polynomial, and 10th degree polynomial, if it has to agree with the 10 degree I mean higher degree polynomials obviously have large curvatures and all, and once they have to agree to certain function values, then there are going to be wild oscillations about the points. So, there is a limit, and that is why the virtue of using only lower order polynomials for interpolation. Higher order polynomials, higher degree polynomials as an interpolation function for construction of function approximation are not necessarily a good thing. So, this particular example I picked up just to highlight this point, that more the higher degree polynomial interpolation is not necessarily the best thing. Very soon we hit the law of diminishing returns. So, the Runge function that I used here is 1 over 1 plus 25 x squared, and we approximated its values at by polynomial interpolation. So, uniform sampling, uniform spacing of sampling points or nodes of interpolation, they cause huge errors between the nodes. At the nodes obviously they agree because the polynomial interpolation constraint has been imposed. So, there is no error or there is no problem with that, but in between nodes of interpolation there are large oscillations, and no way we can consider that interpolation function or interpolation model approximation is anyway close to the original function, although they match exactly at the nodes. So, although the Weierstrass theorem and by basic linear algebra we know that it is possible to approximate as closely as possible the any function, finite function over a finite range by using polynomial, suitable polynomial approximation, but the details are not known, and that still remains an unsolved problem. How to choose the nodes of interpolation, how to choose the nodes for developing polynomial interpolation, that will be the best possible optimal location of points. So, we do not know the exact solution yet, but we do have some idea of what should be a better solution, what would be a better solution rather instead of using indiscriminate uniform sampling of data points. And it so happens that very interesting thing, that it so happens that the roots of Chebyshev polynomials, they constitute a nearly optimal set of points which serve as excellent location for the nodes of interpolation. So, these are the Chebyshev polynomials of respective degrees, increasing degrees. So, T 0 is a constant line at 1. So, that is the first degree 0th degree constant part term. T 1 is a linear term, and T 2 is a quadratic, T 3 is a cubic, and so on. And they are all they have very beautiful, I mean very smooth, very nice looking functions, but they also have very interesting property that the roots of these Chebyshev polynomials are nearly optimal locations for the nodes of polynomial interpolation. So, for 10th degree polynomial I need 11 nodes. So, I would just pick up the roots of 11th degree Chebyshev polynomial and locate that. So, what are Chebyshev polynomials? Chebyshev polynomials are a family of orthogonal functions. Those are defined for x between -1 to +1 bounded range. Now, that can be scaled, I mean these functions can be scaled and the roots can be accordingly scaled up outside the range, and they can be generated recursively from the lower degree terms. So, first two members of the family are simply 1 and x. So, T 0 the constant term 1 and T 1 is a simple x term, and higher degree terms are related to two preceding lower degree terms as T n nth degree Chebyshev polynomial is derived from n plus 1th degree polynomial and n minus 2th degree polynomial as twice T n minus 1 minus T n minus 2. So, that is a Chebyshev polynomial has its own theory and very interesting development, but that is just not much of interest for our purpose as far as nodes of location of nodes of interpolation are concerned. So, coming back to the Runge function and approximation that you see here. So, the other function non-uniform 10th degree polynomial approximation, non-uniform sampling points, those non-uniform sampling points correspond to the location of roots of Chebyshev polynomial. And if I use those roots of Chebyshev polynomials, you can see that the polynomial interpolation, 10th degree polynomial interpolation is reasonably well behaved, and it can be considered, and certainly it can pass off as a reasonably good approximation for Runge's function. And the same 10th degree polynomial using uniform sampling points, and the sampling points are not very different. I mean, they are this very slight shift in sampling points, and the effect that they have on the quality of approximation is just amazing. So, the location of nodes of interpolation is very, very crucial, and the same thing, I mean, I would urge all of you to please keep this picture in mind, and when we construct approximation, finite element approximation, we will be discussing about nodes, although we will not be we may not be devoting too much time on the mesh generation and what is the best good mesh, or how to generate the good quality mesh. You can keep this particular aspect in mind. The location of nodes has a very important implication on the quality of approximation that we develop. So, that is for the polynomial interpolation using only function values. So, as we saw in the approximation of Runge function, if we concentrate only on the function values, we can possibly have a very large errors in between the nodes, because there is no constraint on the derivative, there is no constraint on how the approximation function approaches the function value at the nodes. So, if we try to improve this situation by constraining not only the function values, but also the derivative functions, then that model is referred to as Hermite polynomial interpolation. So, a better constrained approximation can be constructed by imposing constraints on the derivatives of the approximation function in addition to the function values of function at the nodes for interpolation. So, at the nodes we will look at not only the function values, but also the derivative of the functions. So, slopes of the function. So, constraints on the derivative of the approximating function may be same as the derivative of the original function if it exists, or some other suitable value may be assumed. So, if the derivative is already defined, then it can be used, or we can impose some other we may impose something which is which may be able to provide a better constraint on the approximation. So, once we have these two, I mean, now we will look at this situation. If there are n number of nodes, then if there are function values and the derivative that is available at each node, then we are looking at 2n number of terms, 2n number of constraints conditions are available, and if there are n plus 1 number of nodes, then I am looking at 2n plus 2 number of constraints conditions that are available, and with these 2n plus 2 number of conditions available, I can evaluate 2n plus 2 number of coefficients and 2n plus 1 2n plus 2 number of coefficients would be sufficient to uniquely define a 2n plus 1 degree polynomial interpolation, and that is how we work out. And obviously, the formulation is little bit more tedious, more involved compared to simple function interpolation, but it is very easy to formulate and for construction, and we can define a function phi as a similar to what we have as the roots of the nodes, phi x as a function n plus 1th degree polynomial x multiplied x minus xi product of x minus xi terms, and then construct two sets of polynomials based on the derivatives and Lagrangian interpolation, corresponding Lagrangian interpolation. And then we can combine these, and we can have the suitable polynomial interpolation by based on the linear combination of these two sets of polynomial functions h and h cal h, and again based on interpolation of first term is provides the interpolation of the function values, second summation provides the interpolation of derivative values at the nodes, and together this complete interpolation model provides a better model for function approximation, which is relatively smoother, more smooth than the interpolation model derived only on the basis of function values. So, you can see that while if I use a 2.2 node model, the Lagrangian interpolation or simple polynomial interpolation would fetch me only a first degree polynomial interpolation, whereas if I use Hermite polynomial, then I am looking at 4 constraints for 2 nodes, and then I can actually look at a cubic interpolation polynomial between 2 nodes. So, the higher degree of smoothness of the function approximation is obviously provides a advantage in certain cases, and of course, it comes at the cost of increased computations. So, wherever it is justified, it is a good model to adopt. So, piecewise cubic Hermite interpolating polynomial is a useful tool for populating data between two consecutive data points, two consecutive data pairs while preserving the trend. That is another interesting property of piecewise cubic Hermite interpolation. Cubic Hermite interpolation, as I said, between two data points, between two nodes. So, we can have a cubic polynomial. Now, piecewise cubic polynomial has this very useful property that it does not change the trend of data between the interpolation. So, that has a very useful property, and it can be harnessed for wherever the need be. So, another source of another way of interpolation is cubic spline interpolation, and that we will discuss in our next lecture. Thank you.